So our next Nano Fellow is Eli Wilner. He's a PhD student of Professor Eran Rabbani. And he's going to talk about non-Markovian effects and multiple steady states in non-equilibrium quantum systems with electron-phonon interactions.
Okay, thank you very much. First, I would like to thank the organizer for the opportunity of speaking here. I only have 15 minutes, so after you finish reading the title, then maybe I have only half of the time. This work is done with Professor Eran Rabbani, which is currently not here, but he sends his best regard. And the title is Non-Markovian Effect with... I will send him back. Okay, so basically after Alon's talk, then actually saved me some time of talking about a few things regarding quantum transport and ballistic transport. Basically, the outline I will talk about open quantum systems and the specific model we are considering. I will talk about some approaches that have been studies in this particular model and some unsolved questions which are still debatable, some formalism that we are taking and some information we can learn, and then I'll show some results for this particular formalism. So basically, what system are we looking at? So basically, nowadays we can fabricate and we can construct a single molecule that can perform some molecular junctions. This can be, most of the experimental guys here can explain better how exactly to do this. This is basically some open quantum system where basically the molecule is confined between some two metal leads to create some molecular junction. And while you're going to nanometer scale, then basically you're talking about the quantum transport where Alon just mentioned. The formalism that basically deal with some such models is basically the Landauer approach, where basically you can see some quantum conductance. Basically, this system are open quantum system, and by open quantum system, I mean that you have some, in our case, the molecular occupied between the two metals, which is basically a quantum dot, basically coupled to some external environment and interact with this environment. Now, you have to excuse me, I'm a theoretician, so I'll have to put some equation in my slides, but I'll try to make it as simple as possible. So basically, what exactly this system is under condition of, this is basically, we're looking at the non-equilibrium condition. So just to go back to some simple statistical mechanical features. So basically, equilibrium statistical mechanics tell us that if you want to look at a Boltzmann statistics, so basically each expectation value that you're looking at, some operators, they basically will not involve with time. So basically, the average remain constant in time. When you're looking at the out of the equilibrium, it means that basically your initial density matrix, or initially the probability matrix, which is basically the same, does not commute with the Hamiltonian, and which basically means that you'll have some average that has time dependence. When you're looking at long times, meaning time goes to infinity, then your system will go to some new equilibrium. Basically, what we are caring about is a non-equilibrium condition, whereas as mentioned before, you can take basically your device and apply some gate voltage. Basically, this mean that you apply some different chemical potential, or in physics we mean different chemical potential, basically the energy to move or insert some electron to our bath system. So basically, we are looking at non-equilibrium, which is basically a very hard task to basically calculate this kind of stuff. So what exactly the model are we looking at? So as I said, we're looking at the quantum dot. So basically, it's a very small quantum dot, which means that if you basically contact it to some two metal devices, each time you charge your molecular dot, then it basically accompanied by a change of the geometry in the nuclear, which, as we all know from simple solid-state physics, will acquire some vibration oscillation, and this will be coupled to our quantum dot. This is basically also known as the Holstein Model. So once a vibrational degree of freedom is added to our system, then basically we are coupling our quantum dot to some external, not just the metal leads, but basically to our to some phonons in the system. So basically, this is how the system looks at. If one is considered basically how the Hamiltonian is, you don't have to go into the details. Basically, the Hamiltonian basically defines our system. So basically, you have the On the left here, basically the free energy of each type of the system. You have the quantum dot, which is basically a single level, which has some energy. You have the non-interacting, based on Landauer's Fermi. So you can look at the left and right lead as a basic non-interacting fermionic bath. You have the phonon where they have the free energy. And basically what is interesting, the coupling energy, which is basically written down here. The first one is the coupling between the leads and the quantum dot. And the second one is basically the quantum dot coupled to the vibrational degrees of freedom. Now, the problem is that you don't know how to solve this kind of Hamiltonian. Well, each approach that you want to try to solve this, you couldn't. You have to apply some, or either perturbation or either numerical exact method in order to solve some, I don't know, some features you want to know about the system, for example, conductance, or even you want to know the current or the population of the system on the quantum dot. You can't do this. Basically, if you would extract one of these coupling, then basically you can solve it analytically, but this is not the system we are looking at. So some approaches that we're taking for this method, basically there are some steady state approaches. So you have the non-interacting system, which is basically the Landau, which Alon mentioned. You have the master equation in Redfield. In the brackets, you see some groups that are considering these methods. You have the non-equilibrium Green's function method, which already in the 50s, Keldysh did this kind of stuff. You have this famous article by Amir Wingren. You have Abraham Nitzan, which is in the physics department. And you have also a group that looks at the steady state approaches. And you have the time-dependent approaches, where basically there is no analytical approach to this stuff. You have the real-time path integral, which has been done in our group and with collaborating some group at Columbia University. You have the MCTDH. I'm not going into the details, but just that you know there are other time approaches, where the two first approaches are numerically exact ones. And you have another approach that we are considering in our group, which is basically some Kadanoff-Bayam approach to 2 times non-equilibrium Green's function. For those of you who don't know exactly what all these things mean, you can forget about it. It doesn't really matter, but there are some approaches that are taken. And the thing is that each approach has its own limitation. Because if you look somewhat at this kind of diagrams, well, basically here I plotted the energy scales relevant to the system. So basically the y-axis is the temperature scale. The gamma here is a typical energy. This is the unit we are working on, which is basically the lead and the dot coupling. And you have the electron-phonon coupling. So basically you can look at some regimes. Well, if you're looking at a ratio that the electron-phonon coupling is very small compared to the leads, and basically in a perturbative quantum regime, this you can solve in all kind of stuff, basically in the non-equilibrium Green's function or diagrammatic Feynman approach, which only good for this kind of regimes. If you go into strong coupling regime, then basically all your approach is limited either by a dynamical sign problem if you're using a time-dependent approach. And basically what you want to do is you want to take to develop some theory that will be accompanied, that will be satisfying all these kind of regime. Well, this is a problem. So basically we want to know how can we look at a time-dependent approach, which will basically tell us everything about the system with all kind of regimes of parameters that we are looking at. So specifically what I'm going to talk about is a certain project that we did in this kind of model, where basically I want to know the steady state behavior. Well, I'm presenting here some result that has been published by the article written down here. This is not my friend Uri Banin, so I don't know whose Skype is it. So basically I'm presenting some... You want to answer, Uri Banin? No? So basically I'm presenting some results regarding some steady state property of this kind of system, which involves electron-phonon interaction. This is a paper that recently published in Physics Rev B Rapid. And this is, the plot here shows the current as a function of time with a numerical exact approach, where basically they claim that they have reached steady state with the current, and they see some so-called bistability or multiple steady state in the current. Basically, if you look, the inset of each graph shows the long tail steady state behavior of the current, which is, you can debatable whether it's a real steady state or it's a numerical error. And the red and black curves basically correspond to an occupied and unoccupied, initially occupied and unoccupied dot, which is basically looks as if the current for the both system doesn't reach the same steady state. Basically, there is a multiple steady state. Now, the question is it really true? does a steady state or multiple steady state exist, or even a steady state basically exists in such kind of system where basically we don't know how to answer it. So basically this project is involving something which is called the steady state behavior. So basically what I want to do is to answer this question is imagine that you have this whole kind of degrees of freedom in the full Hamiltonian that I already wrote, but basically what I want to know is to understand how does the single quantum dot, or basically how does, from all the degrees of freedom, basically just the quantum dot behavior as a function of time. So what I want to do, I want to take all the degrees of freedom, trace them over, and just study our small reduced density matrix. So basically what you have to do in open quantum mechanics, you take your full Hamiltonian. Let's say you have the quantum dot, we call it the system, which is the relevant part which we are interested in, and you have the bath, which is basically the environment we are coupling the open quantum system. So basically you trace out all the degrees of freedom from the full density matrix, and basically you are left with the small degrees of freedom. So as I said, you have to address your Hamiltonian by partitioning it into several subspaces, basically the system, which is the relevant part. And the way to do it is to define some projection operator. So it takes the full Hamiltonian and basically project it into the small one. Now, the full density matrix is one for quantum mechanics. The equation of motion is basically the Liouville-von Neumann equation of motion. So if you apply this projection and rewrite again the equation of motion for the reduced density matrix, then one is going to get something which is a well-known formalism, which is called Nakajima-Zwanzig equation. So basically, the horrible equation that's written here inside of the box is basically the equation of motion for only the quantum dot, which is basically a single quantum dot, which can have only two states, which is basically occupied and unoccupied. This is a 2-by-2 matrix. Or if you're considering, let's say, of the population of the dots, so basically only interested in the diagonal terms of it. And if we're looking at this equation, so basically we can understand each term exactly. So basically the first term is what is called the Liouvillean of the system, which is basically only the commutation relation of the quantum dot with some operator. This would have been if the system was uncoupled to any environment. It basically would have propagated by an oscillation term. The second term, which is the theta of t, is basically the propagation of the initial correlation of the system, which is basically taken as uncorrelated at time t equals 0, meaning that both systems are in equilibrium, and at time 0 we turn on our interaction and then let the system evolve. So basically this theta term can be dropped. You can show it analytically that if you're starting with a non-correlated system, that basically doesn't matter. And you have the last term, which we call kappa, which is basically tell us nothing. But if you look at this term, that it looks that the time evolution of the system basically always involves propagating time and depending always on the history of what happened due to the interaction. Basically, this is the memory kernel that appears in our system. Now, the question is, where does the memory comes from? Why does we have it? So, yes, that's it. 2 minutes. Wow. Okay. So, any questions? Okay. So, I'll try to go faster. So, basically, where does the memory come from? So, imagine you're going to your bathtub and you have a rubber duck and you put it inside your bathtub. And at some t equals 0, which is basically picture 1, then you apply some force on the rubber duck. So basically, let's say you push it downward, then you have some ripples and some water waves that will be addressed on, and then it will, at time 3, let's say, it will hit the edges of the bath and will return back to the duck, and at time 5 the duck will again rise up, and so on until time 6, that basically the system will go to some steady state. So basically, what happened is the duck at time 5 basically raised up because of some perturbation or some force we applied at time 2. Basically, this is a non-Markovian effect. This is a classical duck. It's not a quantum duck. But imagine that you now take the whole bath and you trace out the degrees of freedom. This is basically what we did in the equation. So imagine your quantum duck, your classical duck is a quantum dot, and you trace out, you don't know anything about you're blind to see the bath because you traced out all the degrees of freedom. So basically, each time the evolution of the duck happens, it basically depends on everything that happened before. This is called the non-Markovian effect, which is unlike the regular quantum master equation where the memory is local in time. Basically, a Markovian effect happens in this kind of systems. So I'll go fast on some of this stuff. Basically, you can learn a lot about this about this memory kernel non-Markovian effect. Basically, it can tell you everything you want to know about the system, and I didn't say anything about what the system, and I didn't even, it doesn't depend on any Hamiltonian basically that you write in. Basically, the memory kernel gives you all the properties you need to know about the steady state. First of all, he shows that you can solve it. I'm not going to the math, but basically you can solve the memory and show that within the steady state, basically the equation reduces to some eigenvalue problem. You can show there is, so basically there is only one unique steady state. And there can be no degenerate steady state in this kind of system. Basically, the article I showed you before where they showed two steady state basically is not true. It's not physically true. The question is what happened when you apply all the electron-phonon interactions. So basically, I'm going to show you a result, just 1 minute. So basically, this is the Landauer approach where Alon talked about. So on top of it, I'm showing you all the matrix element which involve the memory. So you see even for a non-interacting system where you don't have all the electron-phonon coupling, so basically you can see there is a finite memory and non-Markovian effect, which basically enable us to know the time evolution of the density matrix to long time. So if the memory is here, this is on a logarithmic scale, so if the memory here goes to 1 gamma, which basically our unit, you can propagate your density matrix from the time that the memory kernel basically goes to 0. So basically you can solve the equation analytically from the time that you know the non-Markovian effect. So basically the approach that we have taken out is basically solve the memory kernel for the system for whole type of regime for short times, and basically when the memory kernel or the non-Markovian effect is stopped, basically you can propagate your system even to reach steady state. And when you have this is in the electronic case, when then you apply electron-phonon interaction, we discover something interestingly, that basically you can have a bistability. You can have multiple steady state. Not in the electronic one, this was proved analytically 2 slides ago, but basically if you're starting with different initial condition on the phonon bath, meaning if you take your nuclear configuration, basically you can shift it at the initial time, or basically if it stays on its equilibrium position, then basically you can have 2 multiple steady state. And all this, I won't go inside because why does it happen? Because it will take me a long time to explain. We don't have time. But basically, this is not reachable by any analytically or numerically method taken. So basically, a steady state, which is basically this is the main thing on our project, is multiple steady state can occur due to the non-Markovian effect, but only in the phonon initial condition, but not in the electronic one. And I know it was very fast, so in this time I'd like to thank you.